Hello everyone, thanks to everyone for watching this video. My name is Qida. I am an architect and engineer. Today's video is titled Lower Bound Method, and it is going to introduce how to use the lower bound method to estimate the bearing capacity of strip foundations. I am going to give you an overview of what I am covering in today's video. First at all, it is a bit of background to the topic, and then focus on the cohesion model and the friction model. Many of the traditional methods of geotechnical engineering design are based on the concepts of plasticity. In plasticity solutions, only the soil strength needs to know, rather than the full stress strain. Critical state soil strengths are comparatively easy to determine, since they are relatively insensitive to state paths and stress history. In this video, we will introduce lower bound solutions. The lower bound theorem states that if a system of stresses within the soil mass can be found which is in equilibrium with the external loads and body forces, and nowhere violates the failure criterion for the soil, then the external loads and body forces represent the lower bound to those that will actually cause collapse. Any error will be on the safe side, since it may be that a different system of stresses will carry even higher loads without violating the failure criteria. In short, if it can be shown that the soil can carry the loads, then it will. Now we know the lower bound theorem. Next, we can apply the lower bound theorem to calculate the collapse loads of idealized shallow strip foundations or footings. There are two cases. One is a cohesion model, one is a friction model. Both of two models, the soil is assumed as weightless material. Now we will explore the collapse of a strip footing using the cohesion model. This figure shows our representation of a 1 meter section taken out of a long strip footing resting on a material with constant strength tau maximum equal to Cu. The contact stress on the foundation has been increased to P, at which collapse occurs. The soil above the footing plane has been assumed to make no contribution to the strength of the construction, and it has been replaced simply by its dead weight Q. The foundation has been damaged by interposing a frictionless surface Vx between the footing and the soil. Suppose that some active zone A exists under the footing, and that passive zones P exist on either side. The principal stress direction, therefore, rotates through an angle of 90 degrees from zone A, in which it is vertical, to zone P, in which it is horizontal. To interpret the rotation of principal stresses, we can see the stress discontinuity. This figure shows that two neighboring zones Q and R of cohesive soil can be in equilibrium across a discontinuity XX, such that their mole circles are shifted slightly apart, implying a shift of stress and stress direction, while remaining tangential to the limiting envelope Cu. The mole circle for the zone Q is shown with its center at Q, while that for the zone R moves an arbitrary small distance ds along the sigma axis to point R. The discontinuity XX between the zones must be in equilibrium, so the shear and the direct stresses sigma x and tau x must be the same in each zone. This means that the common point x shared by the two mole circles must represent the boundary between the zones. In the mole circles, directions on mole circles rotate twice as fast as their corresponding directions in the material. According to the sine rule, the principal stress increase is 2 times Cu times sine d theta. If d theta is very small, then sine d theta is approximately equal to d theta. So ds becomes 2 times Cu times d theta. It is easily integrated to solve large rotations. This very simple result links the shift of Mohr circle very closely to the rotation of the principal stress direction in a plastic cohesive material, which is everywhere in limiting equilibrium. Using this equation, the stress increase of the cohesion model is equal to pi times Cu, which is the limiting shift in Mohr circles from A to P. But the limiting Mohr circle for zone P was already known. This enables the desired limiting Mohr circle for zone A to be fixed. The estimate of stress P is equal to Q plus 2 plus pi in a bracket times Cu. Thus, we obtain the bearing capacity factor Nc equal to 2 plus pi. Next, we will analyze the friction model to estimate the bearing capacity of the strip foundation. This figure shows our conventional representation of a 1 meter length of strip footing, which is supposed to receive no benefit from adjoining sections. Therefore, it might be taken out of an endless footing. The stress between footing and soil has been increased to P, at which point the overburden pressure Q is pushed into the air and the footing collapses. The foundation has been slightly damaged for analytical purposes by passing a frictionless surface Vx between the footing and the soil. Some simple active zone A must exist under the smooth footing, together with passive zones P under the overburden. The principal stress direction rotates through an angle 90 degrees from vertical in A to horizontal in P. To interpret the rotation of principal stresses, we can see the stress discontinuity. This figure shows a discontinuity XX between two slightly different zones, Q and R. There is an infinitesimal rotation and shift of principal stresses across XX, but the discontinuity would not be stable unless the two zones shared a common boundary stress, sigma x, tau x, which must be a common point on their Mohr circles. Q and R mark the centers of the two Mohr circles, and the shift QR is the increased ds in the mean stress. Angles are doubled on the Mohr circle. Applying the sine rule to triangle QXR, we can simplify the expression and obtain ds over s equal to 2 times tangent phi times d theta. This can be easily integrated between two regions 2 and 1, between which a large rotation theta minus 0 occurs in the principal stress direction, all the intervening states being tangential to the friction line. This links the shift in the center of Mohr circles to the rotation of the direction of the major principal stress, on the assumption that each Mohr circle is in limiting equilibrium by being tangential to the friction line tau equal to sigma tangent phi. Using this equation, the average stress SA of the friction model is equal to SP times exponent of pi times tangent phi. For the Mohr circles, the average stress SP and SA are shown here. Then we substitute SP equation into P equation. After simplification, we obtain the bearing capacity factor NQ. This is an important factor to estimate the bearing capacity of strip foundations. From conclusions, what we learned? A lower bound solution, based on a system of stresses which is in equilibrium and doesn't violate the failure criterion for soil, tends to err on the safe side. The lower bound technique considers only equilibrium and yield. Okay, thanks to everyone for watching my video today, and I do hope you found the video informative and that you learned some things from it. If you do have any questions, then you can write comments and messages. I am happy to answer any questions. Thanks for your watching.